All right, so here we're looking at a one-dimensional finite element method. This is chapter 3 in the textbook. And the basic idea here is to discretize a region. And of course, this 1D approach is going to be really important in our learning of the finite element method because the methods are pretty much the same in the other dimensions as I mentioned. So we take our time in this process, and then we speed up as we go along. But yeah, the goal here is to discretize a region. We're going to express the displacement field in terms of values at discrete points. And this is the difference we talked in the initial lecture about. You could formulate the finite element method in terms of force or displacement. And modern techniques use displacement mostly. Stiffness and load concepts are developed using potential energy or Galerkin approaches. Okay, and this is a thing that you need to understand if you're going through the textbook. There are two approaches that are presented. Okay, so there's a total potential energy approach used to formulate the method. You can also do it through this Galerkin approach. And Popov-Galerkin, we'll talk about him later briefly, but he was a mathematician that formed this, it's a variational, called a variational approach. That's very deep into the mathematics. I used to teach a lot of the Galerkin methods, and so basically what you find in the textbook, if you're following along on that and getting confused, they're presenting both of these simultaneously because a lot of the modern research and techniques uses Galerkin method. It's kind of like it's like the most general advanced idea that most people are using these days. However, when you're learning it, the total potential energy is typically taught first because the Galerkin is very abstract, it's very mathematical, and it's hard to understand. So it's nice that the book actually presents both of those. You see that actually you get the same result from both of them. So that's kind of interesting too. I used to teach a lot more of these like simultaneously, and I've gone more towards the potential energy. Teaching it, I found students could grasp it better, and I present sort of short overviews of the Galerkin as I go. So that's kind of, if you're trying to wonder and figure out why the book does that, that's why it is. And then we are also going to consider boundary conditions. So for the one-dimensional problem, we have to get these mathematics down, okay? And we have to specify what we're going to do. So here we have displacement, we have stress and strain. Notice that they're all in terms of x. And so while this was a vector before, so we had a u, I guess u1, u2, u3, or ux, uy, uz. Now it's just ux. It's one value. And the same thing with stress and strain. There's only one component of that. Tractions, force, everything is just fx, or just a function of x. The strain is simple. That's what we've been using probably in your previous classes. So we basically just have the strain times some material property. Young's modulus here gives the stress. Okay, and the strain, which you already know, is du dx, and all those other terms that we saw before are 0. So this is a very simple case we're looking at. Now, it's kind of confusing here because what this is actually looking at is we're going to be developing the mathematics for a truss element first. Okay, and what's confusing about it is that it's a 1D, but it has cross-sectional area that we can consider. And that allows us to consider trusses of different cross-sectional areas. So we can do thick or thin trusses. So it's kind of confusing because it's actually, when you think about it, it kind of adds a dimension, a y dimension, for example, or a cross-sectional dimension. But it's almost just like a material property at this point. But that gives us the dV idea also, the volume, because we have an area, cross-sectional area times a length. Okay. So the loading, we talked about this before. We have F, T, and point load. The body force is distributed acting on every elemental volume of the body and has units force per unit volume. Self-weight due to gravity in this example is an example of a body force. Okay, so if you had gravity acting on this particle, you could have a body force there. You remember that the traction force is a distributed load acting on the surface of the body. Previously, we defined the traction force is defined as force per unit area. However, in this 1D problem, the traction force is defined force per unit length. Okay, this is done by taking the traction force to be the product of the force per unit area with the perimeter of the cross section. Okay, we will get into that later. Frictional resistance, viscous drag, and surface shear are examples of traction forces in one-dimensional problems. We have P of I acting at a point I, and then we consider this bar. Okay, so we're getting into element division and node numbering. So this is a bar that we're going to be looking at. We have our traction forces, you can see here, acting on this surface. We have body forces that are acting due to gravity, and we have these actually point loads that are described here. And the first step we're going to do is discretize this, discrete number of elements, each having a uniform cross-section. So this is really important. So we have our mathematics in terms of stress, strain, displacement. We're now discretizing, and we took this shape, which has curves and is complex, let's say it's complex, and we discretize it into elements, these chunks of material. And you can see it kind of shows the surface. We're losing some ability to describe that nice smooth curve, but we do have a general shape of that thing. Okay, so I mean, at that point, you have error going to introduce in your system at that point. So that's something to remember. But we have these 4 elements. Well, we have 5 nodes, 1, 2, 3, 4, 5. And the elements are numbered with the circles around them. And the nodes are at these positions. They each have a uniform cross-section. So notice that they do all have different cross-sections, but within a single element, it is uniform. All right, so I think this is everything I said already. Traction force is normally treated as constant within each element. That's important because as we go from moving the equations with the integral sign into a discretized, we need some way to handle that integral. And so assuming that they're constant helps us do that. And of course, better approximations are obtained by increasing the number of elements. So we subdivided. In fact, if we subdivided, we could do a lot different cross-sectional areas, right? And so we can make small degradations and increase of length, and so it could more closely adhere to the original shape of the geometry just by subdividing. That's an important point to make. Okay, so we took a rather complicated looking bar, been modeled as a discrete number of elements, each having a simple geometry. The similarity of the various elements is one reason why finite method is easily amenable computer implementation. This is just the intro statement that you'll see in this class, that we start to look at repeated patterns of element types. Really helps us out as we scale this up. All right, so for easy implementation, an orderly numbering scheme for the model has been adopted. In one-dimensional problem, every node is permitted to displace only in the x direction, and each node has 1 degree of freedom. So so what does it mean? So this is the degree of freedom x. Okay, so this node 5 can move in the x, it cannot move in the y. Same way with 4, 3, 2, and 1. Only can move in the x direction. So that's 1 degree of freedom, and the degree of freedom is x. Okay, and so this 5-node finite element model has 5 degrees of freedom. So each one, this is 1 degree of freedom. I'm sorry, this is this is counted as 1 degree of freedom. Okay, so we have 1, 2, 3, 4, and 5 in each node. So for example, if we had for some reason, if 1 was allowed to move in y, and we'll see this when we go to 2D, that would increase the degree of freedom by 1. If these all were fixed, so they could not move in y, but this one could, we would have 5 plus that extra one here would be 6. So that's kind of how you do it. All right, we'll talk about that more later. Now, numbering scheme. This is pretty interesting too. We're now introducing these variables, displacements, each degree of freedom denoted by Q1, Q2, Q3, Q4, and Q5. So there is an x coordinate. Let's see, we can call that typically x or big X, little x. But there's a coordinate, but then this is actually something different. This is actually the displacement. So how much does one move actually? Okay, that's the displacement is different from the coordinate. I think you could agree with that. Coordinate is where it's located in space. Displacement is how much it's moving. Okay, so this is actually also stored in a column vector, Q, and it's called the global displacement vector. Okay, this term global has now entered into the vocabulary. I'm going to wait to talk about that until a little bit later. But we also have the same thing for the load vector. Okay, the global load vector, we could have forces, so I could be moving this node, for example, Q1, I could be pushing on it, maybe Q5 is a better example. I could be pulling Q5 with a set displacement, so I say you're going to move 1 meter down, or I could say I'm going to pull on this 1 Pascal or whatever it is, I'm going to pull on it, okay, and displacement just happens to pop out as a function of how stiff everything is. So those are some important notations. All right, so now here we go. This is the element connectivity. Each element has 2 nodes. All right, so let's look at element 1. We have element 1, that's equal to 1 and 2. These are 2 nodes that belong to element 1. All right, and you can see if we were to simplify this problem, we would take this picture down here and draw it right here. We have node 1, 2, 3, 4, and 5, right? And here is element 1, and that has nodes 1 and 2 in it. This is the Q1 right here. We have Q2 here. And this is all in the global numbering system. Global force, global displacement, global numbering. Global numbering. I like to think about fine elements as kind of 2 levels. We have global and we have local. Global and local, there's 2 levels, and we can reach down into the local, we can reach up to the global. If we're down at the local, we can go, you know, it's almost like a video game, and there's these levels that you're going back and forth, up and down. Okay, so global numbering is here. There's something called local numbering, and that's with this concept of what we call the master element. We'll talk about that a lot in this class. But the master element now, for this truss, this 2-noded, 1-dimensional truss, has 1 element and 1 node and a second node. Here's the element number. And you see here we're using lowercase q and lowercase f. So these are all the local numbering. We have the connectivity, all right, that's shown here. So we have element 1 connects nodes 1 and 2, 1 and 2. Element 2 connects nodes 2 and 3, 2 and 3. Element 3 connects, here's element 3. What nodes are connected? Well, 3 and 4. Here is what really interesting thing here though. So 3 and 4, what is the local numbering of node 1? Well, the local numbering corresponds to 1. So 3, if you sort of take this global element chunk and sort of move it down here, 3 is aligned with 1 and 4 is aligned with 2. Isn't that interesting? So Q2 for element 3, Q2 corresponds to global displacement Q4. Okay, so where that comes, why is important, is because all these things are connected, right? And so if you look at element 4, then you know Q1 is the same as 4, and so what we're going to end up doing is adding these little q's from all the shared nodes together. So that's kind of how we compute things down at the local level, and then we move it up in what's called the assembly process and put it all together for global. So this chart is really interesting. This is you really want to understand this table here. Okay, global, this is connectivity. Connectivity matrices in the fine element are fundamental. Connectivity establishes the local and global correspondence. All right, so we're going to wrap that up. Hopefully I did a decent job at explaining that and showing the picture of that. We're now going to move into something really exciting, and that's connected to the master element and this idea of interpolation, foundational idea here for fine elements, and that is shape functions. We'll do that next.